Hi, the discussion in this video is going to be about calculation of potential energy using the concept of potential. Now, I've been repeating this several times, and I'll say this one more time, that potential at a point, if it is, let's say it is equal to V, and if we place a charge Q at this point, then the change or the increment in potential energy of the system is Q times V, and this fact can be used for calculating potential energies of all kinds of systems. Now let's start with something we already know, so that we kind of gain the confidence that this is a correct technique. And so to start with, we'll use this concept of potential to determine the potential energy of a system of two point charges. So let's say we have 2 point charges. The first one is Q1 and the second one is Q2, and they are placed at a distance r apart from each other. Now we already know that their potential energy would be equal to 1 by 4 pi epsilon naught Q1 Q2 by r. Now that's something we already know. Now we'll be using the concept of potential in making a calculation of this potential energy. And to do that, what we need to do is we need to assemble the system one charged body at a time. And as we assemble the system, at every step when we introduce a charge, there is a certain change in potential energy. We add up all the changes in potential energy and arrive at a magnitude of the final potential energy of the system. Of course, we start with the assumption that initially, when there were no charges present, the potential energy was obviously zero. So let's start assembling this system. The first charge we bring in, now let's forget about this. There is no charge anywhere in our observed universe, and we bring in a charge Q1 to this point from infinity. So we started at infinity, brought this charge Q1 to this point initially. Now in this step, this is the step 1 in assembling the system, and in this step 1, what we have seen is that there is a change in potential energy delta U1, which equals 0. Why? Because the point where we have placed Q1 had zero potential to start with. There were no charges around here, and therefore at this point the potential was 0. We brought in a charge Q1 to this point, and therefore the change in potential energy is Q1 times the potential, which is 0, and therefore delta U1 is 0. Now let's introduce the second charge in step 2 of the process. Now charge Q1 is already there. Charge Q1 is already here, and this is the other point at a distance r from it. Now we pick up a charge Q2 at infinity and bring it all the way to this point. Now in this step of the process, again there is a change in potential energy, let's say delta U2, and that would be equal to the potential at this point before the introduction of charge Q2. And what was that potential? 1 by 4 pi epsilon naught Q1 by R. That was the potential at this point before the introduction of Q2. Now we multiply the potential with the charge Q2, and that gives us the change in potential energy of the system on introduction of charge Q2. So the system has now been assembled, and these are the changes in potential energies in the various steps while assembling the system. Now the potential energy of this system U would simply be equal to the sum of the changes in potential energies while the system was being assembled. And so you just add them up. You have 0 and this quantity here. U therefore equals 1 by 4 pi epsilon naught Q1 Q2 by R, which we already know is the correct value of potential energy of this system. So now this is a fairly handy process for calculating potential energies, but not for a system of a large number of point charges. You know, if you recall that question we discussed, that problem we discussed about charges kept on the vertices of a cube, and there were 28 charges there, and if we were to solve that problem using this process, we would have 28 such calculations, and the potentials at those points would be fairly interesting to calculate as well. So this process is not advisable for systems which involve a fairly large number of point charges, but the process becomes very useful when we are talking about continuous distributions of charge, and I will demonstrate that calculation in our next bit of discussion. What we are going to now do is we will be calculating the potential energy of a single continuous charge distribution. Of course, we are aware that a single continuous charge distribution is a collection of a large number of small charge elements, and since we have a large number of charge elements which are interacting with each other, there is some potential energy associated with a continuous charge distribution. So the first such charge distribution we are taking up is a uniform spherical shell. Now with a uniform spherical shell of charge, let's say we have this shell and it carries a charge Q, it has a radius R. It's a shell, so all the charge resides on the surface. There is no charge inside. Doesn't matter whether inside has a material in there or not. The charge resides entirely on the surface. No charge is there inside this shell here. Now in this kind of a scenario, how do we calculate the potential energy? Because you have lots of small charge elements and all of them are interacting, and therefore you'd have an enormously large number of pairs, and you can't really calculate potential energies of all those pairs and add them up and so on. So the process of calculation of potential energy learnt in the previous videos is not very useful here, whereas the calculation of potential energy, the way we have discussed so far in this video, is going to work fairly well. Now how we are going to do it is, we are going to assemble this charge Q on the surface a little bit at a time, and we'll calculate the change in potential energy in every step and then do a summation of it. Now let's see how this works. What we do is we go all the way up to infinity. We go to infinity, pick up charge dq. Of course, I'm starting with the assumption that initially there is no charge. So forget this charge here. There is no charge. What we have here is, let's say, a balloon or something. So this is a balloon perhaps which has no charge on it. We go to infinity, pick up charge dq from there and bring it to the surface and spread it uniformly on the surface. So we've gone to infinity, we've picked up charge dq, brought it to this sphere, and we've spread it uniformly on the surface. So the charge here is now dq, and then we again go to infinity, pick up another dq and spread it uniformly on this surface. After a little bit of time, let's say we've built up a q amount of charge on this shell. Now once again, after the charge has been built up to q, we again go to infinity, pick up dq and spread it uniformly all over it. Now in this particular step here, in this last step, when the charge here was q and we went to infinity, took charge dq and spread it all over, in this step there's a certain change in potential energy involved. Let's say it's du. Now because of the presence of charge q here, the potential is 1 by 4 pi epsilon naught q by r. That's the potential here. Now we have placed the charge dq at a location where this is the potential. So the change in potential energy will be potential times the charge we have placed at that location. So this is the change in potential energy in introducing a further charge dq here. Now we are introducing charge dq on and on and on in all these infinite steps, building all the way up to q. So what we need to do now is to calculate the potential energy. We need to add up all these changes. We need to do a summation of all these changes in potential energy, which is easily done using a bit of calculus. So we are going to integrate this quantity here, 1 by 4 pi epsilon naught r q dq, and the charge was being built up from 0 all the way up to q. Now 4 pi epsilon naught and r are constants, so they move out of the integration process, and we calculate u therefore as 1 by 4 pi epsilon naught r and the integral of q dq from 0 to q. Now that integral is easily evaluated. You'll probably be able to do this in your sleep with your hands tied behind your back. Q square by 2, 0 to q, and so u equals q square by 8 pi epsilon naught r. Now interestingly, this is the potential energy of a single charged body. Now when we calculate the potential energy, of a single charged body, this potential energy is called its self energy, because it's the energy of the body itself. Now when we have several such charged bodies and they interact with each other as well, the potential energy resulting from that interaction would be called potential energy of interaction. So when you have a system of several charged bodies, to calculate their potential energy, to calculate the potential energy of their system, what you need to do is you add up all the self energies and also all the potential energies of interaction, and we'll explore that process going further in this video. So this is how you calculate potential energy of a uniform spherical shell of charge. Now we move on and talk about a solid sphere of charge. Now how does a solid sphere of charge differ from a shell? Let's first understand this fact. So we're dealing now with a solid sphere of charge. Now the difference between a spherical shell and a solid sphere lies in the fact that the solid sphere has charge distributed in its entire volume, not just on the surface. So we now have charge distributed all over the surface of this body. The charge that the body carries is Q, and we are interested in calculating the self energy again. Now for a sphere, the calculation gets a little more interesting, because in case of the shell, the charge was always distributed on the surface, and that was at a distance r from the center. But in the solid sphere, charge distribution is there in the entire volume. So the addition of charge in this case is a little bit different. What we will do with the sphere is, as we add charge to the sphere, we'll be adding it in spherical shell layers. So to calculate potential energy, we add charge onto the sphere in spherical shell layers, and as we add layer after layer on one top of each other, the sphere gets constructed, and we calculate the changes in potential energies in all those steps. Now let me explain this process to you. To start with, we will need to understand what's the volume charge density here. Now the volume charge density will be charge Q divided by 4 by 3 pi r cube. That's the volume charge density here. Now let's see what is the process of constructing this. How we construct this sphere is, we start when there is no sphere, there is no charge, and we start bringing in little bits of charge dq, having this amount of density per unit volume, and we assemble layer after layer. Now let me construct one such layer. Now this layer has a radius r, and has a thickness dr. So this layer we are bringing in. This layer of charge is actually a spherical shell of charge. So what we've done is, there was a small sphere of radius r having this volume charge density. Then we went to infinity, picked up some amount of charge, and added a layer, a spherical shell layer on top of that smaller sphere. This layer has a thickness dr. So we picked up some material from infinity carrying this volume charge density. We added this layer of material on top of the sphere that we have already constructed. So we've got this layer, and we keep adding such layers one on top of each other, and as we add layer after layer after layer, the entire sphere gets constructed. This is what is being done here. Now what's the volume of the material that we have added here? That volume dV is 4 pi r square dr. Now how do I calculate this volume? Take this spherical shell out, flatten it up. Now as you flatten it up, it becomes a plain sheet having an area 4 pi r square. So this one, once we take it out, flatten it up, it has a surface area 4 pi r square and a thickness dr. Now the volume therefore would be area times that thickness. So 4 pi r square dr would be the volume. Since this is the volume charge density, the amount of charge dq that we have added will be rho times this dv, and this comes out to be q by 4 by 3 pi r cube times 4 pi r square dr. So the amount of charge dq that we've added here is the 4 pi cancels, and so we have 3q by r cube into r square dr. So that's the charge dq that we have added. The charge that was already there was the charge in the sphere of radius r. So the charge that was already in there was volume 4 by 3 pi r cube times the volume charge density, which is q by 4 by 3 pi r cube. So the amount of charge that was already present was q times r cube by capital R cube. So that's small q, the charge that's already in there in the sphere of radius r, and we've added this amount of charge as an additional layer in our first in our step of addition of charge that we are looking at. Now in this process, since charge q was already there, the potential at the surface was obviously 1 by 4 pi epsilon naught times this charge q r cube by capital R cube. So 1 by 4 pi epsilon naught into the charge small q here divided by the radius, which is r. That's how you calculate potential on the surface of a solid sphere. Potential on the surface of a solid sphere would be, if it has a charge q and a radius r, then the potential on the surface would be 1 by 4 pi epsilon naught q by r. Now small q, this is the charge q, and the radius here of course is r. So this is the potential. Now at a location where this is the potential, we have added a charge dq, this amount of charge. So the change in potential energy will be 1 by 4 pi epsilon naught q r square by r cube, this potential, times dq, which is 3q r square dr by capital R cube again. So this is du. Now U, the total potential energy, will be a summation of all the du changes, and so the summation of course is easily achieved using integration, and we take the constants out. Q square 3 by 4 pi epsilon naught r to the power 6, all this moves out, and we integrate r to the power 4 dr, and the integration process is done for the initial value of r, that's 0. We start building with 0 material there. There was no charge initially, there was no material there, so we started with 0 and we built it up all the way up to capital R. Now this integral will be, easy to see, this integral will be capital R to the power 5 by 5, and so U will be 3 by 5 times Q square by 4 pi epsilon naught R. This is the potential energy of a solid sphere of charge. Now only spherical charges exist for which we are able to easily calculate self energies. For other shapes the task gets that much more complex. With spheres the geometry is very simple and there is plenty of symmetry to work with, but for other charge distributions this task is not that simple, and therefore rarely, if ever, any questions are likely to be asked with other geometries. So that's all about the formula derivations for self energies. Now we use the ideas that we have just acquired, we've just learned, in calculating potential energies of systems of charges. Now I'll give you an example of how potential energy of a system of charges can be calculated using these ideas that we have just learned, we've just acquired. Hope you've taken a screenshot of this, and we then move on and discuss the calculation of potential energy of a system of charges. Now let's consider a system of two spherical bodies. The first one is a shell having a radius r1 and a charge q1. The second body is a uniform solid sphere of charge carrying a charge q2 and having a radius r2. The distance between these spheres, this is a solid sphere, the distance between their centers is small r, and we are told that small r is much larger than r1 and also much larger than r2. Now we are interested in calculating the potential energy of this system. So how do we go about doing that? As we've been doing in our discussions today so far, what we do is we assemble the system one charge at a time and calculate the potential energy change in every step. So think of it this way. Let's say initially there was nothing here, and the first thing we did was we assembled this charge Q1 here. We brought this charge Q1 here, has a radius R1. Now this is step 1 of the process. Now in this step, now initially there was no charge, now we have this charge. When we add this charge here, then the change in potential energy of our system in this first step is simply the self energy of this sphere, and that self energy will be Q1 square by 8 pi epsilon naught R1. So that's the change in self energy in this first step. Let's move on and assemble the second charge now. Now in step 2, the first charge, the shell of radius R1, is already there. Now we are bringing in at a distance R a solid sphere carrying a charge Q2 and having radius R2. Now in this step there is a change in potential energy. Now there are actually two changes that have happened here. Once we place this charge here, the self energy of this charge, that is one of the changes in potential energy. The self energy here is 3 by 5 times Q2 square by 4 pi epsilon naught R2. This is one change in potential energy. Also, we place charge Q2 in the potential of charge Q1. Now at this location, I am assuming this R to be very large and R2 to be very small. So practically Q2 is a point charge. We have placed almost at the center. If we are looking at the interaction between the two, the potential throughout this body can be assumed to be very nearly equal to the potential at the center. So the potential due to this sphere at the center of this sphere, that potential is 1 by 4 pi epsilon naught Q1 by R. This is the potential at the location of the second sphere due to the first sphere. Now the first sphere was already there, so this potential was already there at that location. We multiply this potential with charge Q2 to get the change in potential energy because of the interaction between the two bodies. And this quantity is the potential energy of the interaction between the two bodies. Now, to calculate the potential energy of the system, all we do is add delta U1 and delta U2, and we have the potential energy of the system. So the total potential energy now comes out to be Q1 square by 8 pi epsilon naught R plus 3 by 5 Q2 square by 4 pi epsilon naught R2. These two are the self energies, and then we have this potential energy of interaction, which is 1 by 4 pi epsilon naught Q1 Q2 by R. So remember, these are the two self energies, and this here is the potential energy of interaction. So this is how potential energies of various systems can be calculated. And now with charges, what we've done is we've learned how to calculate potential energies of various kinds of systems. This is one example where we've learned how to calculate potential energy. Now if we can do this here, we can do it in just about any other case using the same kind of process, same kind of technique. Now, once we know how to calculate potential energies, we can solve a whole lot of problems which involve the concepts of mechanical energy. If we have charged objects which are thrown against each other, then using concepts of principles of conservation of mechanical energy, for example, we can calculate how much close they get to each other, etc., etc. And those calculations are much like the calculations that we have learnt in the earlier classes when we used to solve problems on conservation of mechanical energy. No difference here. The only thing that changes is the calculation of potential energy because of the presence of charges. So all those problems come within our range, and perhaps in one of the future videos we'll take up some such problem solving as well. Once we've covered some more ground on the ideas, the concepts, then we'll take up maybe one or two videos where I highlight some problem solving using the concepts we've been learning about electrostatics. Bringing this video to a close here, because I think we've covered fair ground, and also the video is beginning to get very long. I'm being criticized by some people that my videos are very long, which is the case. I definitely concede, but then lectures on a subject cannot be much smaller than, let's say, 40 odd minutes. If I break them up into smaller bits, some of the continuity is lost, and therefore I have settled on this rough 40 to 50 kind of minutes interval, which seems to be fairly ideal for me to be able to communicate an idea or to completely with continuity. Of course, there will be some exceptions. There will be times when I'll go longer than this. There will be times when the videos will be shorter than this. But that's pretty much the optimum that I have worked out. Thank you very much for watching this video. Please send in your suggestions and let the feedback come. Also, do like, share and subscribe these videos so that some of the ideas we are sharing can be shared with more people. That's the idea in starting this channel. Hopefully physics can be communicated to larger number of people so that they develop this understanding. Because of lack of quality teaching in various parts of the world, a lot of people who are interested in learning the subject are not able to do it, and this channel is one effort from my side to teach physics at that level.